The first humans to reach Mars might never see Earth again. Not because they don't want to, but because coming home from Mars isn't like catching a return flight from vacation. It's one of the most complex engineering challenges we've ever considered, wrapped in physics that work against us at every turn. Here's what nobody tells you about Mars missions. The journey there is the easy part. Getting back? That's where everything falls apart. And the reasons why reveal just how unprepared we are for what might be humanity's greatest adventure. Let's start with something simple: distance. Mars sits roughly 140 million miles from Earth on average. But that number is deceptive because Mars and Earth are constantly moving, orbiting the Sun at different speeds. Sometimes Mars is 34 million miles away. Other times it's 250 million miles distant. This creates what engineers call launch windows, specific periods when the planetary alignment makes travel feasible. These windows open once every 26 months. Miss your window, and you're waiting over 2 years for the next one. You can't just decide to leave Mars whenever you want. The universe doesn't work that way. The trip to Mars takes 6 to 7 months using current propulsion technology. That's half a year confined to a spacecraft smaller than a studio apartment, bombarded by radiation, watching Earth shrink to a pale blue dot behind you. Your muscles will atrophy despite exercise. Your bones will weaken. Your vision might deteriorate from pressure changes between your brain and eyes, a condition called spaceflight-associated neuroocular syndrome. But you'll arrive eventually. You'll step onto Martian soil, plant your flag, take your photos for the history books. Then reality sets in. The return journey requires just as much fuel as getting there. Actually more, because now you need to escape Mars's gravity and accelerate to the precise velocity needed to intercept Earth's orbit 7 months later. We're talking about enormous quantities of rocket propellant, far more than any spacecraft could carry from Earth. This is where the math becomes brutal. To return from Mars, you need at least 1,200 metric tons of ascent propellant. That's roughly the weight of 200 adult elephants. Except it's highly refined rocket fuel that doesn't exist on Mars. You can't mine it. You can't extract it from rocks. You have to make it. And making rocket fuel on another planet? We've never done that before. Not even close. The leading proposal involves something called the Sabatier reaction, a chemical process that converts carbon dioxide and hydrogen into methane and water. Mars has plenty of CO2 in its atmosphere. About 95% of it is carbon dioxide. The hydrogen, though, needs to be brought from Earth or extracted from Martian water ice. This sounds reasonable until you examine what's actually required. The process demands enormous amounts of energy, specialized equipment that must function flawlessly in Mars's hostile environment, and access to water. Martian water exists, certainly, buried in ice deposits beneath the surface. But reaching it means drilling tens of meters down through frozen regolith, an energy-intensive operation that requires robotic systems we haven't fully developed yet. Consider the engineering challenge. You need power systems robust enough to run for years without maintenance, in temperatures that swing from 86 degrees Fahrenheit to -284. You need drilling equipment that can penetrate ice-hardened soil contaminated with perchlorates, toxic salts that damage machinery and poison humans. You need chemical processing plants that can operate in near-vacuum conditions with dust storms that last months. And every single component must work perfectly. There's no calling for replacement parts. No repair technician arriving next week. You're 140 million miles from the nearest hardware store. But let's say you solve the fuel production problem. You've got your 1,200 metric tons of methane and oxygen sitting in tanks, ready to launch. You're not done. Not remotely. The return vehicle itself needs to survive 16 months on Mars before you can use it. 16 months of temperature extremes, radiation exposure, and dust accumulation. Martian dust isn't like Earth dust. These particles are roughly 3 micrometers across, smaller than pollen, with sharp crystalline edges and a slight electrostatic charge. They stick to everything like microscopic styrofoam peanuts and work their way into every seal, every joint, every moving part. This dust destroyed the Opportunity rover in 2018. A global dust storm coated its solar panels so thoroughly, the rover lost power and never recovered. That was a machine designed specifically for Mars conditions. A human return vehicle, with its complex engines and life support systems, offers thousands of additional failure points. The dust problem illustrates something crucial about Mars. The planet actively fights human presence. It's not neutral, it's hostile. Take the atmosphere. At 610 pascals of pressure, less than 1% of Earth's, it might as well not exist. You can't breathe it. It won't protect you from radiation. It can barely slow down incoming spacecraft. Yet it's thick enough to carry global dust storms that can reduce sunlight by 60% for months at a time, with peaks where illumination drops to 1% for up to 3 months. During those storms, solar power becomes useless. Nuclear power helps, but nuclear reactors require maintenance, cooling systems, and shielding, all adding weight to your mission. Weight matters because every kilogram you land on Mars is a kilogram you somehow need to lift back into space. Which brings us to the landing problem. We've successfully landed rovers on Mars. The Perseverance rover weighs about 1 metric ton, but a human return vehicle, that needs to weigh 50 to 100 metric tons depending on the design. Our current landing technology, parachutes, airbags, sky cranes, has reached its limit. These systems work for small payloads, but fail at scale because Mars's thin atmosphere provides almost no drag for slowing down heavy vehicles. Engineers know this. They've known it for decades. We don't have a solution yet. So even if you manufacture fuel on Mars, even if your return vehicle survives intact, you still need to solve how you landed something capable of carrying humans back to orbit in the first place. It's a circular problem where each solution depends on solving something else first. Let's talk about timing again, because this might be the cruelest constraint. You arrive on Mars, you need to wait for the next Earth-Mars launch window, that 26-month cycle. Except you can't leave immediately when the window opens. You need to ensure your fuel production is complete, your vehicle is functional, your supplies are sufficient. The optimal mission profile has astronauts spending 500 days on Mars before attempting return. That's 16 months. 16 months in reduced gravity, that's 38% of Earth's. 16 months of radiation exposure equivalent to getting a hip X-ray every single day. 16 months where any medical emergency, appendicitis, broken bones, dental problems, becomes a potential death sentence because you have no real medical facilities and no way to get help. The communication delay alone changes everything. Mars is far enough that radio signals take between 3 and 22 minutes to reach Earth, depending on orbital positions. A conversation with mission control isn't a conversation. It's sending a message and waiting up to 44 minutes for a response. If something breaks, if someone gets injured, if a critical decision needs to be made, you're on your own. The people on Earth can offer advice, but by the time their words arrive, your situation may have completely changed. This isolation does something to human psychology that we're only beginning to understand. Studies of crews in isolated environments, Antarctic stations, submarine missions, space station stays, show that after about 6 months, problems emerge. Crew cohesion deteriorates. Depression and anxiety increase. Minor personality conflicts escalate into major problems. A Mars mission isn't 6 months, it's 3 years minimum. 3 years in a confined space with the same handful of people, no privacy, no escape, watching Earth become an insignificant blue-green dot in the sky. Psychologists call this the Earth out of view phenomenon, and we have no idea how humans will truly respond to it over years. Some researchers believe the psychological challenges might be even more dangerous than the physical ones. You can engineer solutions to radiation or design better life support systems. But human nature? That's harder to fix. And on Mars, a psychological breakdown doesn't just affect one person. It threatens the entire crew's survival. The radiation exposure deserves its own examination because it's not something you can really shield against, not with current technology. During the journey to Mars, astronauts will absorb about 0.66 sieverts of radiation. NASA's career limit for astronauts is 1 sievert. A Mars mission uses up 2/3 of an astronaut's lifetime radiation budget before they even arrive. On Mars's surface, despite being on solid ground, radiation continues at 0.67 millisieverts per day. That's 200 millisieverts per year, roughly 40 times what you'd receive on Earth. This radiation comes from galactic cosmic rays and solar particle events. On Earth, our magnetic field and thick atmosphere protect us. Mars has neither. Its magnetic field died billions of years ago, and its atmosphere is too thin to provide meaningful shielding. You're exposed, constantly, to high-energy particles that slice through cells and damage DNA. The immediate risks include increased cancer probability, cardiovascular disease, and cognitive decline. But there's something worse: kidney damage. Research published in 2024 found that prolonged exposure to the radiation levels present on Mars and during space travel causes serious, potentially irreversible kidney damage. Your kidneys might simply fail before you make it home. You can't shield effectively against this radiation without adding massive amounts of mass to your spacecraft or habitat. Lead works, but lead is heavy. Water works even better, but water is heavier. Every kilogram of shielding is a kilogram of fuel you can't carry, food you must leave behind, or equipment you can't bring. Some mission designs propose using Martian regolith, the dusty soil, as radiation shielding by piling it on top of habitats. This helps, but it doesn't protect you during the 7-month journey to Mars or the 7-month return trip. Those months in space represent your highest radiation exposure, and there's no regolith to hide under when you're millions of miles from any planet. The physical deterioration goes beyond radiation. Mars's gravity is 38% of Earth's. Initially, this seems manageable. You can move around, work, function. But over months, your body begins adapting to this lower gravity in ways that make returning to Earth increasingly difficult. Your bones lose density at about 1 to 2% per month. Your muscles atrophy despite exercise. Your cardiovascular system recalibrates to pumping blood in reduced gravity, becoming less efficient at fighting Earth's pull. After 16 months on Mars, your body will have fundamentally changed. Whether it can change back is unknown. We have no data on how humans respond to partial gravity over extended periods because we've never tried it. The astronauts on the International Space Station experience microgravity, essentially weightlessness, not the intermediate state that Mars provides. Some researchers believe that partial gravity below 0.4 g is insufficient to maintain human physiology long term. Mars sits at 0.38 g. You're right on the edge of what might be sustainable, and we won't know until someone tries it and either succeeds or fails to readjust to Earth gravity. If you can't readjust, if your body has adapted too completely to Mars, then Earth becomes uninhabitable for you. You'd arrive home unable to stand under your own planet's gravity, your heart struggling to pump blood, your bones too fragile to support your weight. At that point, coming home might kill you faster than staying on Mars. This raises an uncomfortable question that mission planners rarely discuss publicly. What if the first Mars astronauts are physiologically incapable of surviving the return journey? What if their bodies have changed too much? Then those astronauts aren't coming back, not because we don't want to bring them home, not because the technology failed or the fuel production didn't work, but because their own biology has betrayed them, adapted to an alien world in ways that make Earth itself alien to them. And we're only beginning to understand why that might be inevitable. Your mind breaks before your body does. That's what keeps Mars psychologists awake. We can measure bone density loss. We can track muscle atrophy. But how do you quantify the moment a human mind decides it's had enough of red dust and thin atmosphere, and a sky that's never quite the right color? Picture yourself on Mars for a moment. Earth hangs in your night sky, when you can see it at all, as nothing more than a pale blue dot. You knew this intellectually before you left. You saw the simulations. You understood the distances. But knowing and experiencing are violently different things. The Earth out of view phenomenon sounds almost poetic until you're living it. Astronauts on the International Space Station can look down and see their home planet filling their view, massive and immediate. They can spot their home countries. They can watch weather systems move across familiar continents. That psychological anchor, that visual reminder that home is right there, keeps them tethered. You don't have that on Mars. Earth becomes an abstract concept, a memory of a place that might as well be fictional. And your brain wasn't designed for this kind of isolation. The communication delay makes it worse. When you're having a crisis, and you will have crises, you can't talk to anyone about it in real time. Every conversation with Earth involves a 20-minute delay each way, minimum. When Mars and Earth are at their farthest orbital distance, that delay stretches to 44 minutes round trip. Try having a conversation with 44 minutes between each exchange. It's not a conversation. It's leaving voicemails for each other, stretched across the solar system. Your family can't comfort you. Mission control can't advise you in real time. A therapist can't talk you through a panic attack. You're on your own in ways that no human has ever been on their own before. This isolation triggers something researchers call behavioral health deterioration. The term sounds clinical. The reality is people breaking down in ways that threaten the entire mission. Studies of Antarctic research stations, our closest analogue to Mars isolation, reveal patterns. First comes the euphoria phase, excitement about the mission, wonder at the environment, camaraderie with crewmates. This lasts weeks, maybe months. Then comes the reality phase. The environment stops being novel and starts being oppressive. Small annoyances with crewmates become major irritations. The same faces every day, the same limited spaces, the same conversations, the same food, the same routine, day after day after day. Some people develop subsyndromal depression. Not quite clinical depression, but a persistent low mood, loss of motivation, sleep disruption, difficulty concentrating. Others experience anxiety disorders. Still others show cognitive changes, slower reaction times, impaired decision-making, memory problems. And here's what makes this particularly dangerous. You're in an environment where a single bad decision kills everyone. A depressed astronaut who loses focus for 30 seconds might forget to properly seal an airlock. An anxious crew member might make an impulsive choice during an emergency. Someone with impaired judgment might misread a critical system warning. The psychological screening for Mars missions will be intense. But screening can't predict how someone's mind will respond to months of Martian isolation. The human brain is adaptable until suddenly it isn't. Interpersonal conflicts become existential threats. In Antarctic stations, people can request transfer or evacuation if situations become unbearable. On Mars, there's no evacuation option for 26 months. You're stuck with whoever you're stuck with. A personality clash that would be merely annoying on Earth becomes catastrophic on Mars. Researchers studying long-duration isolation missions identified leadership conflicts as one of the highest-rated concerns. Who's actually in charge when mission control is 20 minutes away? What happens when crew members disagree about critical decisions? Cultural misunderstandings compound these problems. International crews bring different communication styles, different approaches to hierarchy, different expectations about privacy and personal space. These differences create friction in the best circumstances. In the pressure cooker environment of Mars, they can explode. The Mars One project, that ambitious plan to establish a permanent Mars settlement, failed partly because simulations revealed how quickly things deteriorate. One simulation found that crop growth large enough to feed the colony would produce unsafe oxygen levels in the habitat. The team would suffocate on their own success. Another study predicted that without dramatic improvements in equipment reliability, colonists would starve to death. But the psychological findings were arguably worse. Test crews in isolation facilities on Earth developed conflicts so severe that mission parameters had to be abandoned. And these were people who knew they could leave whenever they wanted. Remove that safety valve, and things get darker. Medical emergencies add another layer of psychological pressure. You're 7 months from the nearest hospital. If something goes wrong with your body, your crewmates have to handle it with whatever training and equipment they brought. Appendicitis on Earth means a routine surgery and a few days of recovery. Appendicitis on Mars means a crew member performing emergency surgery on you in a cramped habitat with limited anesthesia while everyone else watches and hopes nothing goes wrong. If your appendix ruptures before the surgery, sepsis will kill you. There's no medevac. There's no calling in a specialist. You live or die based on luck and whatever medical skills your crew happens to possess. The psychological weight of this responsibility is crushing. Every crew member carries the knowledge that they might have to watch their friends die from treatable conditions. Or worse, that they might be the one performing the failed surgery, the one who couldn't save someone. Sleep disruption amplifies everything. Mars has a day length of 24 hours and 39 minutes, just different enough from Earth's day to gradually desynchronize your circadian rhythms. This phenomenon, called circadian drift, causes chronic sleep deprivation. You're constantly slightly jet-lagged, never quite rested, always operating at reduced cognitive capacity. Poor sleep impairs emotional regulation. Small frustrations become rage. Minor worries become paralyzing anxiety. You're tired, stressed, isolated, and responsible for keeping yourself and your crew alive in an environment that's actively trying to kill you. Now layer on the knowledge that you might not be able to go home, that your body might be changing in ways that make Earth uninhabitable for you. That decision to come to Mars, which seemed brave and historic when you made it, starts feeling like the worst choice you've ever made. Some mission planners have seriously proposed one-way Mars missions as more realistic than round-trip missions. Former astronaut Buzz Aldrin advocates for Mars-to-stay missions, where the first astronauts sent to Mars never return. The logic is straightforward. Eliminating the return journey cuts mission costs and complexity dramatically. But consider the psychological implications. You're asking someone to voluntarily exile themselves from Earth forever. To never see a forest again, never swim in an ocean, never feel rain on their face. To accept that everyone they know will age and die while they're on Mars, and they'll never attend another funeral, never hug another friend, never return home. That's not exploration, that's permanent exile. And the psychological toll of that choice, made years before launch but fully experienced only after arrival, could break even the most resilient minds. The isolation creates something researchers call third quarter phenomenon. In long-duration missions, psychological problems peak around the three-quarter mark. You're past the initial excitement, too far from the end to see relief coming, and the cumulative stress has worn down your psychological defenses. This is when people break. For a Mars mission, the third quarter point comes during your surface stay. You've survived the 7-month journey. You've been on Mars for months. You're exhausted, psychologically strained, and you still have months of surface time left, plus another 7-month journey home. This is when mission-threatening psychological crises are most likely to occur. And if someone does have a complete psychological breakdown on Mars, what then? You can't restrain them humanely in reduced gravity. You can't sedate them indefinitely. You can't send them home early. They remain a danger to themselves and everyone else for the duration of the mission. The psychological screening process will attempt to identify people prone to these breakdowns. But extreme isolation affects everyone differently. Someone might be perfectly stable in every test environment and still fall apart on Mars. We won't know until we try, and by then it's too late. Some researchers propose psychological countermeasures. Regular Earth-like experiences through virtual reality, carefully structured schedules with variety, mandatory exercise routines, defined personal space, periodic special events to break monotony. These might help, But they're guesses based on limited data from Antarctic stations and submarine crews. Environments far less isolated and dangerous than Mars. The fundamental problem remains. Human psychology evolved for Earth. We're adapted to 1G gravity, 24-hour days, breathable atmosphere, open spaces, and social connection with a broader community. Mars provides none of these things. Your mind will try to adapt, but adaptation has limits, and we don't know where those limits are because we've never tested them under genuine Mars conditions. The first Mars crew will be psychological guinea pigs, in addition to everything else they'll be testing. If your mind breaks on Mars, can it be fixed when you return to Earth? If you develop anxiety disorders or depression or cognitive impairment during your mission, does recovery happen automatically when you come home? Or do some psychological changes become permanent, rewiring your brain in ways that never fully reverse? We don't have answers to these questions. We have educated guesses and concerning data from incomplete analogues. The truth is, we won't know until someone goes to Mars, stays there for months, and tries to come back. And this brings us to a question mission planners rarely discuss in public. What happens if the psychological toll makes astronauts decide they don't want to come back? Not because they can't physically return, but because they've mentally adapted to Mars in ways that make Earth feel wrong, alien, overwhelming. Your mind can trap you on Mars as effectively as your body can. And unlike bone density loss or muscle atrophy, there's no exercise routine to prevent it. You either stay sane or you don't, and you won't know which until you're already there. Millions of miles from help, with nowhere to go but forward. But here's something nobody talks about in those glossy Mars mission promotional videos. Your body is going to betray you in ways you can't prepare for. And I'm not talking about the obvious stuff like muscle loss or bone density. I'm talking about what happens to your cells at the molecular level when you're bombarded with radiation equivalent to a daily hip X-ray for months on end. Mars has no magnetic field. Earth's magnetic field acts like an invisible shield, deflecting most of the charged particles streaming from the sun and cosmic rays from deep space. On Mars, you get hit with all of it. The surface radiation is 0.67 millisieverts per day. That doesn't sound like much until you do the math. Over 500 days on Mars, you're looking at 335 millisieverts. Add the journey there and back, and you're approaching 660 millisieverts total. NASA's career limit for astronauts is 1,000 millisieverts. You're going to burn through 2/3 of your lifetime radiation allowance in a single mission. If you want to go to Mars twice, you can't. The second trip would push you past safe exposure limits. This isn't like getting a sunburn that heals. Radiation damage accumulates. It breaks DNA strands. Your cells have repair mechanisms, but they're not perfect. Every repair has a small chance of error, and those errors accumulate into mutations. Some mutations do nothing. Some kill the cell. Some turn it cancerous. The radiation models predict a 5% increase in cancer mortality risk from a Mars mission. That's the central estimate. The upper confidence interval goes to 10%. 1 in 10 chance of dying from cancer caused by your trip to Mars, and that's just mortality. Morbidity, getting cancer but surviving it, runs higher, potentially 10 to 20%. But cancer isn't even the scariest part of radiation exposure. Your cardiovascular system takes damage too. Radiation increases your risk of heart disease, stroke, and circulatory problems. Your brain accumulates damage that causes cognitive decline. memory problems, reduced processing speed, difficulty with complex reasoning. NASA ranks these radiation effects as red risks, the highest priority category, because they're likely to occur and their impact is severe, and you can't shield against it effectively. Water provides some protection, but you'd need meters of water surrounding your habitat to reduce radiation to safe levels. That's not feasible with current technology. The mass alone would make launching impossible. Regolith, Martian dirt, works better, but burying your habitat under several meters of dirt creates its own problems. How do you get in and out? How do you repair external equipment? What happens if your life support fails and you need to evacuate quickly? Some mission designs propose underground habitats, using lava tubes or digging into cliff faces. That helps with radiation, but now you're living in a cave on Mars. No windows, no views of the landscape, just artificial light and rock walls for months. The psychological impact of that compounds all the isolation problems we already discussed. Your kidneys face particular danger from the combination of radiation and microgravity during the journey. Research from June 2024 found that serious health risks emerge with respect to kidney function the longer someone is exposed to the conditions astronauts would experience during a Mars mission. Your kidneys aren't designed for extended periods in low gravity. They filter your blood based on pressure gradients that assume 1 g of gravity. In microgravity during the journey, and 0.38 g on Mars, those pressure gradients change. Kidney stones become more likely. Kidney function deteriorates, and radiation damages kidney tissue directly. If your kidneys fail on Mars, you're dead. There's no dialysis machine, no transplant possibility, no way to treat kidney failure in a Mars habitat with limited medical equipment. Let's talk about that medical situation more carefully. What medical equipment can you bring to Mars? You're limited by mass constraints. Every kilogram of equipment is a kilogram that could be food, water, or spare parts for life support. So you bring the essentials: basic surgical tools, medications, diagnostic equipment. But you can't bring an MRI machine. You can't bring a full surgical suite. You can't bring specialists in every medical field. What happens if someone needs their appendix removed? You have to perform surgery in Mars gravity with whoever on your crew has the most medical training. That might be someone with basic EMT certification, who took a crash course in emergency surgery before the mission. The surgery happens in your habitat, which isn't a sterile environment. It's the place you've been living for months. Dust gets everywhere on Mars. We'll get to that problem soon, and that dust is now in your surgical field. What if the surgery goes wrong? What if they develop sepsis? You have antibiotics, but bacterial infections in space behave differently than on Earth. Some bacteria become more virulent in microgravity. Their resistance to antibiotics increases. Your immune system is compromised by radiation exposure and the stress of living on Mars. An infection that would be treatable on Earth might kill you on Mars, or say someone breaks a bone. In Mars gravity, bones are already weakening. A break is more likely. Setting the bone is the easy part, but proper healing requires the right gravitational loading. Does a bone broken in 0.38 grams heal correctly? We don't know. We've never tested it. The astronaut might heal with a permanent disability, unable to perform crucial mission tasks. Or the bone might not heal properly at all, creating a chronic injury that gets worse over time. What about vision problems? Spaceflight-associated neuroocular syndrome is another red risk. The pressure differences between your brain and eyes in microgravity cause fluid shifts that can damage your optic nerve and distort your eyeball shape. Some astronauts on the International Space Station have developed permanent vision changes. On Mars, you're in 0.38 G, not 1 G. We don't know if that's enough to prevent the syndrome or if you're still at risk. If your vision deteriorates on Mars and you're the pilot for the return journey, everyone's in danger. Here's a question that keeps mission planners awake. What happens if someone dies on Mars? Not theoretically, specifically, what do you do with the body? You can't bury it outside. You'd need to dig in permafrost while wearing a pressure suit. That's incredibly labor-intensive and dangerous. You can't cremate it. You don't have fuel to spare for cremation. You can't send the body home. There's no room in the return vehicle. You'd probably have to freeze it outside the habitat and store it for the duration of the mission. Your dead crewmate becomes a frozen reminder of what went wrong, visible every time you go outside. The psychological impact on the surviving crew would be devastating. And if whatever killed them was infectious, you might have already been exposed in your shared habitat with its recycled air. The medical unknowns extend to basic biology. How does wound healing work in 0.38 grams? How does pregnancy? Some proposals for Mars colonization talk about families and children born on Mars, but we have no idea if human reproduction functions normally in reduced gravity. Can embryos develop properly? Would children born on Mars ever be able to visit Earth? Or would 1 G gravity be too much for bodies that developed in 0.38 G? Every biological system evolved for Earth gravity. Your cardiovascular system pumps blood against 1 G. Your inner ear's balance system calibrates to 1 G. Your muscles and bones build themselves assuming 1 G loading. On Mars, all of these systems are operating outside their design parameters. Some will adapt, some will fail. We won't know which until people try to live there long term. And then there's the Martian environment itself trying to kill you. The atmosphere is 96% carbon dioxide with an average surface pressure of 610 pascals. That's 0.6% of Earth's atmospheric pressure. It's functionally a vacuum. If your pressure suit fails, you have about 15 seconds before you lose consciousness. The carbon dioxide in your blood will bubble out of solution. Your blood won't exactly boil, but the results are just as fatal. The temperature swings are extreme. Mars can range from -284 degrees Fahrenheit to 86 degrees Fahrenheit. Your habitat needs to maintain comfortable temperatures despite these swings while using minimal power. Your pressure suit needs to keep you warm during the cold periods without overheating you during physical labor. The engineering challenges are immense, and any failure means death within minutes. The dust is even worse than the radiation. Martian dust particles are about 3 micrometers in size, smaller than household dust, and they're electrostatically charged. They stick to everything like styrofoam packing peanuts. You can't brush them off easily. They accumulate on solar panels, reducing power generation. They get into mechanical systems with moving parts, grinding away at seals and bearings. They coat your pressure suit every time you go outside. When you return to the habitat, that dust comes with you. There's no perfect airlock that removes every particle. The dust gets inside. You breathe it. And Martian dust contains perchlorates, toxic salts that damage your thyroid and kidneys. About 0.5% of Martian regolith is perchlorates. That doesn't sound like much until you realize you're breathing trace amounts every day for months. The long-term health effects are unknown because we've never exposed humans to Martian dust. The dust also interferes with growing food. Mars colonization plans always include greenhouses where you grow your own food to reduce supply needs from Earth. But Martian regolith lacks organic material. There's no life on Mars to create soil. The perchlorates make it toxic. You'd need to bring soil from Earth or manufacture it somehow using Martian materials. And your greenhouse needs to be sealed against dust while still allowing light in. Any leak and toxic dust contaminates your food supply. Even if you solve the dust problem and grow food successfully, you create a new problem: oxygen. Plants produce oxygen. In a sealed habitat, oxygen levels can rise to dangerous concentrations. Mars One mission simulations found that crop growth large enough to provide 100% of a settlement's food would produce unsafe oxygen levels. You'd need to vent oxygen outside, wasting a resource that's precious on Mars. Or you'd need to grow less food, which defeats the purpose of growing your own food in the first place. Dust storms add another layer of danger. Local dust storms happen frequently. Planet-wide dust storms occur about once every 3 years and can last for months. During the 2018 global dust storm, illumination dropped to 1% of normal levels for extended periods. The Opportunity rover died because dust covered its solar panels and it couldn't generate power. If you're relying on solar power during a global dust storm, you're in trouble. Nuclear power is more reliable, but bringing a nuclear reactor to Mars creates its own problems. The mass is significant. The safety concerns are extreme. If something goes wrong with your reactor on Mars, there's no one to fix it but you, and radiation exposure from a reactor failure would be fatal. Even with nuclear power, a months-long dust storm creates psychological stress. Your world outside is darkness and howling wind. You can't go outside for EVAS. You're trapped inside your habitat with the same people you've been living with for months. The dust is everywhere despite your best efforts. Your food supplies are dwindling, and you know the storm could last another month or 2 months or 3 months. You don't know when it will end. This is when people start making fatal mistakes. Judgment becomes impaired by stress and isolation. Someone decides to check the external equipment despite the storm. They go outside and get disoriented in near zero visibility. They wander away from the habitat. By the time the storm clears enough to search, they're dead, their frozen body half buried in dust somewhere in the Martian landscape. Or someone decides the risk isn't worth it anymore. They've had enough. They're done. In the confined space of a Mars habitat, suicide becomes a realistic concern. You can't confiscate every potential method. The habitat itself could be used, the airlocks, the pressure suits. If someone is determined to end things, they'll find a way. And if they do, the surviving crew members have to live with that trauma while continuing the mission. There's no backup plan. No rescue mission is coming. When the Mars exploration rover Spirit got stuck in soft soil in 2009, NASA spent 8 months trying to free it remotely. They built an exact replica of the terrain on Earth. They tested hundreds of commands. They consulted with experts. Eventually they gave up and Spirit died where it sat. If a human crew member gets trapped, injured, or faces a medical emergency on Mars, you have none of those options. The 20-minute one-way communication delay means real-time assistance from Earth is impossible. Mission Control can't talk you through a procedure. They can't help you diagnose a problem. By the time you send a message describing an emergency and receive a response, 40 minutes have passed. In a medical crisis, that's an eternity. Consider appendicitis. On Earth, it's routine. Surgery takes about an hour. Recovery is straightforward. On Mars, appendicitis is potentially fatal. Your crew includes people with basic medical training, but they're not surgeons. You have medical supplies, but not a full surgical suite. You have pain medication, but supplies are limited. Do you attempt surgery with inadequate equipment and training? Do you let the person die? These aren't hypothetical scenarios. They're real decisions that will have to be made. The Mars Direct mission architecture assumes crew members can handle medical emergencies themselves. The plan includes a small medical facility with surgical tools and supplies. But performing surgery in Mars gravity after months of muscle atrophy and bone loss is nothing like surgery on Earth. Your hands shake from muscle deterioration. Your depth perception is affected by vision changes from radiation exposure. The patient's physiology is altered by months in reduced gravity. Blood pressure is different. Wound healing is compromised. And if something goes wrong during surgery, there's no emergency room to rush to, no specialist to call in, no backup plan whatsoever. Dental emergencies present another nightmare scenario. Tooth infections can spread to your bloodstream and become life-threatening. On Earth, you see a dentist. On Mars, you improvise with whatever tools you have. The Apollo 13 crew faced equipment failures and came home heroes because they made it back alive. On Mars, equipment failure means you die there. Your habitat's life support system has redundancies built in, but redundancy isn't the same as reliability. Every component has a failure rate. Over months and years, failures accumulate. A seal degrades, a filter clogs, a pump motor burns out. On Earth, you replace the part. On Mars, you hope you brought a spare. If you didn't, you improvise a repair with materials you have available. And if you can't improvise a solution, people start dying. The pressure suits are particularly vulnerable. They're complex systems with hundreds of potential failure points. Seals, valves, regulators, heating elements, communications equipment, all of it has to work perfectly every time you go outside. One seal failure, and your suit loses pressure. You have seconds to get back to the airlock before you pass out from hypoxia. If you're too far from the habitat when failure occurs, you don't make it back. The Martian surface is littered with hazards that can damage suits. Sharp rocks, abrasive dust, temperature extremes. After months of use, wear and tear accumulates. Small problems become big problems. Eventually, something critical fails at the worst possible moment. Water recycling systems are another critical vulnerability. The system has to reclaim water from every source. Urine, sweat, humidity in the air, wastewater from washing. The International Space Station's water recycling system achieves about 90% efficiency. That remaining 10% has to come from stored reserves. On Mars, you can't resupply from Earth on a regular schedule. Launch windows only open every 26 months. If your water recycling system's efficiency drops below projections, you run out of water long before the next resupply arrives. You can try to extract water from Martian soil, but that requires working equipment, power, and time. If your water extraction equipment fails, You're rationing increasingly limited water supplies while trying to repair systems with degrading components. The psychological pressure of knowing there's no rescue intensifies every problem. When things go wrong on the International Space Station, crew members know they can evacuate in a Soyuz capsule and be home in hours. That knowledge provides psychological security, even if they never use it. On Mars, there is no evacuation option. When things go wrong, you fix them or you die. That knowledge weighs on you constantly. Every unusual sound, every minor malfunction, every small deviation from normal operations triggers anxiety because it might be the beginning of a cascade failure that kills everyone. The communication delay compounds psychological stress in ways that are hard to overstate. Humans are social creatures. We need connection. We need to share experiences in real time. We need immediate emotional support during crises. Mars communication makes all of that impossible. You send a message to your family. You wait 20 minutes. They receive it. They respond. You wait another 20 minutes. You receive their response. By then, the moment has passed. The emotion has faded. The connection feels hollow. You're having a conversation with the past, never with the present. This delayed communication makes every relationship back on Earth slowly deteriorate. Your partner is dealing with problems you can't help with because by the time you learn about them, they're already resolved or have gotten worse. Your children are growing up without you. You miss birthdays, holidays, important moments. You see them in videos that are already old by the time you receive them. You send messages that arrive too late to matter. Over months, the relationships that anchored your identity on Earth start to feel abstract and distant. You're still technically married, still technically a parent, but those roles become increasingly meaningless when you can't participate in real time. Meanwhile, the relationships with your crew members become everything. You're isolated together in a small habitat. You see the same faces every day. You eat together, work together, exercise together, sleep in adjacent quarters. Every personality quirk that was minor on Earth becomes magnified. Someone chews loudly. Someone talks too much. Someone doesn't clean up after themselves. On Earth, you'd leave the room. On Mars, there's nowhere to go. The habitat is small. Privacy is limited. You can't escape each other. Studies of Antarctic research stations provide some insight into what this isolation does to people, and Antarctic stations have significant advantages over Mars. The environment outside is harsh, but not instantly lethal. Communication with the outside world happens in real time. Rescue is theoretically possible even if difficult, and Antarctic winter only lasts months, not years. Despite these advantages, interpersonal conflicts at Antarctic stations can become severe. People form factions. Resentments build. Small disagreements escalate into major conflicts. In extreme cases, violence occurs. On Mars, all those same dynamics exist, but intensified. The isolation is more complete. The duration is longer. The stakes are higher. A serious interpersonal conflict on Mars can't be resolved by sending someone home early. You're stuck together until the return window opens, which might be more than a year away. If conflict escalates to violence, there's no police to call, no authority to intervene, except your own crew commander, who is also trapped in the situation. One study of cosmonauts identified leadership issues and cultural misunderstandings, as major psychological risks for long-duration Mars missions. Different crew members come from different space agencies with different management styles. What one culture considers normal communication, another considers insubordinate. What one person views as helpful, another sees as micromanaging. These cultural differences create friction that builds over time. The mission commander faces impossible pressures. They're responsible for keeping everyone alive and functional while dealing with their own psychological stress. They have to mediate conflicts while being part of the system that generates conflicts. They have to maintain authority while living in close quarters with people who see them at their worst. They have to make life or death decisions without real-time support from Earth. The psychological burden of command in that environment would break most people. And here's what makes all of this worse. You can't quit. You can't take a mental health day. You can't request a transfer. You signed up for this mission knowing it would be difficult, but knowing intellectually and experiencing emotionally are completely different things. When you're 6 months into an 18-month surface stay and you're exhausted and stressed and you've had enough, you still have a year left. You still have to get up every day and do your job and maintain the equipment and grow the food and exercise to preserve muscle mass and pretend everything is fine during video calls home. There's no option to tap out. Some crew member will eventually reach their breaking point. Maybe they become withdrawn and depressed, doing the minimum required and no more. That puts additional burden on other crew members who have to pick up the slack. Maybe they become angry and confrontational, creating an atmosphere of tension that affects everyone. Maybe they become paranoid, convinced others are plotting against them or sabotaging equipment. In the confined space of a Mars habitat, one person's psychological breakdown affects the entire crew. The Mars 500 experiment, which simulated a Mars mission by isolating 6 crew members for 520 days, found significant psychological effects despite the simulation occurring safely on Earth. Crew members experienced sleep problems, depression, and interpersonal tensions. One crew member became so lethargic, he barely participated in mission activities. This happened in a simulation where everyone knew they could leave if things became unbearable. On actual Mars, that psychological safety net doesn't exist. Now, factor in the physical deterioration happening simultaneously. Your body is slowly breaking down in the reduced gravity. Your bones are losing density. Your muscles are atrophying despite exercise countermeasures. Your cardiovascular system is weakening. Your vision is changing from intracranial pressure alterations. Your immune system is compromised from radiation exposure. You're in chronic pain from muscle and joint problems. You're tired all the time because exercise countermeasures are exhausting and don't fully work. You're dealing with all the psychological stresses while also feeling physically terrible. The cumulative effect of physical and psychological deterioration creates a downward spiral that's difficult to arrest. You feel bad, so you're less motivated to exercise. You exercise less, so you feel worse. Your worsening physical condition increases psychological stress. Increased stress makes sleep difficult. Poor sleep impairs judgment and emotional regulation. Impaired judgment leads to mistakes. Mistakes create more stress. The spiral continues. At some point during the mission, you'll realize with absolute clarity that coming to Mars was a mistake. Not because the mission isn't important or because space exploration isn't worthwhile, but because the personal cost is too high. You've sacrificed your health, your relationships, years of your life, and possibly your ability to ever return to normal life on Earth. And for what? To be one of the first humans on Mars? That achievement starts to feel hollow when you're in chronic pain, psychologically exhausted, and profoundly isolated. But that realization comes too late. You're already on Mars. The return window might not open for another year. Even when it does open, returning to Earth presents its own dangers. The journey home takes another 6 to 9 months. During that time, your body continues deteriorating in zero gravity. By the time you reach Earth, you've spent 2 to 3 years in reduced or zero gravity. The physiological damage might be permanent. Assuming you survive the journey home, re-entry and landing present final hazards. Your weakened body has to endure multiple G-forces during Earth re-entry. Your compromised cardiovascular system has to readjust to Earth gravity. Some astronauts who spent months on the International Space Station needed wheelchairs after landing. You'll have been gone much longer in worse conditions. Walking might be impossible initially. Full recovery might take years, or might never happen. The long-term health effects of Mars radiation exposure will follow you for the rest of your life. Increased cancer risk, cardiovascular problems, cognitive decline. Every ache, every pain, every health problem for the rest of your life will carry the question, is this from Mars? The radiation exposure during the mission was 0.66 sieverts round trip, according to NASA measurements. That's approaching the agency's career limit for astronauts in a single mission. Cancer risk increases 5 to 10%, with confidence intervals suggesting it could be even higher. Some Mars mission advocates propose one-way trips as more feasible than round-trip missions. Buzz Aldrin supports Mars-to-stay missions, where astronauts go to Mars intending to remain permanently. The logic is straightforward. Eliminating the return journey reduces mission cost and complexity. You don't need to manufacture return propellant. You don't need to maintain a return vehicle for years on Mars. You don't need to plan for Earth re-entry. You just need to keep people alive on Mars indefinitely. One-way missions aren't just a theoretical concept debated by space enthusiasts. They represent a fundamental acknowledgement that Mars colonization might require permanent settlers rather than visitors. The Mars One project in 2012 announced plans to send 4 astronauts on a one-way trip by 2025, building the first permanent human settlement using existing technology. The vision collapsed under scrutiny. Researchers at MIT analyzed the proposal and found critical flaws. Without dramatic improvements in equipment life, colonists would starve to death. Crop growth sufficient to provide all food would produce unsafe oxygen levels in the habitat. The settlers would suffocate on their own food supply. That failed project revealed something important. Living on Mars permanently isn't just difficult. It might be fundamentally impossible with foreseeable technology. Every system has to work perfectly for decades, with no possibility of resupply from Earth. One failure kills everyone. Consider what permanent settlement actually means. You're committing to spend the rest of your life in a hostile environment where everything is trying to kill you. The atmosphere is 96% carbon dioxide. You can't breathe it. The average temperature is minus 60 degrees Celsius. You'll freeze without heating. The atmospheric pressure is 0.6% of Earth's. Your blood would boil without a pressure suit. The radiation exposure is equivalent to getting a hip X-ray every single day. Your cancer risk climbs steadily from the moment you arrive. Growing food on Mars presents obstacles that might be insurmountable. The soil contains perchlorates at concentrations around 0.5%. These toxic salts damage your thyroid, kidneys, and cells. Plants can't grow in contaminated regolith without extensive processing. The environment is too cold. Water is scarce except possibly at the poles. Even if you solve these problems, you face the oxygen dilemma that doomed Mars 1. Plants produce oxygen through photosynthesis. In an enclosed habitat, oxygen levels rise as crops grow. Too much oxygen creates fire hazards and toxicity. You need perfect balance between crop production, oxygen generation, and consumption. One calculation error means everyone dies. The equipment challenges for permanent settlement dwarf anything we've attempted. Life support systems must regenerate air and water indefinitely. NASA tests these systems on the International Space Station, but that's with constant resupply missions and the ability to evacuate if something fails critically. Mars colonists have no resupply, no evacuation. When equipment breaks, they fix it with whatever materials they have or they die. Every mechanical system has a lifespan. Seals degrade. Electronics fail. Moving parts wear out. On Earth, you replace components. On Mars, you manufacture replacements from local materials, or watch your colony slowly fail as systems deteriorate beyond repair. Martian dust makes equipment maintenance nightmarish. The particles are about 3 micrometers, incredibly fine. They're electrostatic, sticking to everything like styrofoam peanuts. The dust is composed of iron oxide and silicates. It's gritty. It gets into gears, seals, any moving parts. Everything mechanical on Mars must be sealed against dust infiltration, but seals eventually fail. The dust coats solar panels, reducing power generation. During global dust storms that occur roughly every 3 years, illumination can drop to 1% of normal levels for up to 3 months. The Opportunity rover died in 2018 when a global dust storm buried its panels. Your colony's power system faces the same threat every few years. Medical care on a permanent Mars settlement presents impossible challenges. You have no hospital, no specialist doctors, no diagnostic equipment beyond what you brought, no pharmaceutical manufacturing capability. When someone develops appendicitis, you perform surgery with whatever medical supplies you have. When someone breaks a bone, you set it with improvised materials. When someone develops cancer from radiation exposure, you watch them die because you have no oncology department. The communication delay means Earth-based doctors can't provide real-time guidance. By the time they respond to your emergency call, the patient might be dead. Psychological support for permanent Mars colonists will be minimal to non-existent. The isolation is total. Earth is a bluish-green dot in the sky. Communication has a 20 to 40-minute delay. You can't have conversations. You can't call friends when you're struggling. Video messages take 20 minutes to arrive and 20 minutes for responses. The emotional distance matches the physical distance. Your family and friends are living their lives 140 million miles away. They're aging, experiencing events you'll never share, having relationships you'll never be part of. You're watching them through messages that arrive with geological slowness while you're trapped in a metal can on a dead world. Research on isolation effects doesn't offer comfort. Studies of cosmonauts identified critical psychological factors for Mars missions: isolation and monotony, communication delays, leadership issues, management style differences, and cultural misunderstandings in international crews. A NASA report specified that Mars astronauts need 25 cubic meters of space per person. That's about the size of a small bedroom. You'll spend years or decades in that space with the same handful of people, unable to leave without a pressure suit, unable to go anywhere interesting because everything on Mars is a barren wasteland. The social dynamics of a permanent Mars colony would deteriorate in predictable ways. Small annoyances become major grievances. That crewmate who chews loudly becomes unbearable after the 1,000th meal together. Personality conflicts have nowhere to diffuse. You can't take a weekend trip to clear your head. You can't avoid someone you dislike. The colony is too small. Resources are too limited. Everyone depends on everyone else for survival, which means conflicts can't escalate to separation, but also can't be truly resolved. You're locked in dysfunctional relationships forever. Leadership problems in isolated groups create cascading failures. Someone has to make decisions about resource allocation, work assignments, conflict resolution. On Earth, bad leadership means you quit and find another job. On Mars, bad leadership means the colony fails. Maybe someone hoards resources. Maybe someone makes decisions that favor their friends. Maybe someone cracks under pressure and becomes authoritarian. You have no recourse, no higher authority to appeal to, no escape. You endure bad leadership, or you stage a mutiny in a habitat where everyone dies if cooperation breaks down. The Mars to stay concept assumes problems are solvable through determination and ingenuity. But some problems aren't solvable. They're fundamental limitations of physics and biology. You can't invent your way out of 38% gravity, causing permanent skeletal and muscular changes. You can't engineer a solution to radiation exposure that damages DNA. You can't overcome the psychological toll of permanent isolation through positive thinking. These aren't engineering challenges, they're existential realities of living on Mars. Buzz Aldrin advocates for Mars to stay missions, arguing that one-way trips reduce cost and ensure permanent settlement. But reducing cost by eliminating return capability doesn't make the mission successful. It just means colonists die on Mars instead of attempting to return home. The settlement becomes a graveyard with extra steps. Everyone who goes there dies there, probably much sooner than they would have on Earth, probably after years of declining health and psychological deterioration. The ethical questions surrounding permanent Mars missions are profound. Should we send people on one-way trips knowing they'll likely suffer and die prematurely? Is it ethical to establish colonies that might fail catastrophically, killing everyone? Space agencies operate under informed consent principles. But can anyone truly give informed consent to permanent exile on a lethal world? The psychological impact of knowing you'll never see Earth again, never breathe real air, never feel rain, might only become apparent after arrival when it's too late. Children born on Mars face even darker prospects. They'll develop in 38% gravity. Their bones will form differently. Their muscles will adapt to reduced weight bearing. They might never be able to visit Earth because their bodies couldn't handle the gravity. They'll be Martians, not humans, adapted to a world that's trying to kill them, unable to survive on their species' homeworld. Is creating a generation of people trapped on Mars by their own biology ethical? There's no precedent for this decision. The technology for Mars return missions remains mostly theoretical. Humanity has never launched a spacecraft from Mars. The engineering challenges are immense. You need to manufacture 1,200 metric tons of ascent propellant from Mars resources. That requires extracting over 1,000 metric tons of water from Mars, which exists as ice but must be mined from depths of tens of meters. The energy requirements are staggering. The equipment must function autonomously because humans can't oversee every step. Robots must drill, extract, process, and synthesize propellant over months or years while surviving dust storms, temperature extremes, and equipment failures. One failure in this chain means the return vehicle never launches. The Sabatier reaction offers theoretical propellant production. You extract CO2 from Mars's atmosphere and react it with hydrogen using nickel or ruthenium catalysts at elevated temperatures, producing methane and water. The process is exothermic, releasing energy. You then separate the methane for rocket fuel and electrolyze the water to produce more hydrogen and oxygen. On paper, it works. In practice, you're running a chemical plant on another planet with no ability to repair or replace sophisticated equipment. The catalysts degrade, the reactors corrode, the separation membranes fail. You need backup systems for your backup systems, and every kilogram of backup equipment is payload mass that makes the mission more expensive and difficult. Landing large payloads on Mars remains unsolved. Current Mars landers use parachutes, airbags, or sky cranes. The Perseverance rover weighs about 1 metric ton. Human missions require 50 to 100 metric ton payloads. Mars's atmosphere is less than 1% of Earth's density, providing minimal aerodynamic braking. These large vehicles will fall too fast for parachutes to help significantly. New landing technologies must be developed and tested, probably through expensive, uncrewed missions that fail repeatedly before succeeding. Each failure delays human missions. Each success costs billions. The return journey from Mars to Earth takes 6 to 9 months. During that time, you're back in zero gravity after spending months in 38% gravity. Your body has partially adapted to Mars. Now it must readapt to weightlessness, then readapt again to Earth gravity. The physiological stress might be worse than the outbound journey because your body is already compromised. Muscle atrophy accelerates. Bone density decreases further. Cardiovascular deconditioning worsens. By the time you reach Earth, you've spent 2 to 3 years in reduced or zero gravity. The damage might be irreversible. Earth re-entry presents final hazards. Your weakened body must endure multiple G-forces during atmospheric re-entry and landing. Your cardiovascular system, compromised by years of reduced gravity, must suddenly pump blood against full Earth gravity. Some astronauts who spent 6 months on the International Space Station needed wheelchairs after landing. You've been gone 3 times longer in worse conditions. Walking might be impossible initially. Standing might cause fainting. As your cardiovascular system struggles to maintain blood pressure against gravity, it hasn't experienced in years. The long-term health effects will haunt you forever. The 0.66 sieverts of radiation exposure approaches NASA's career limit in a single mission. Cancer risk increases 5 to 10% with confidence intervals, suggesting it could exceed 20%. Every health problem for the rest of your life carries the question, is this from Mars? Cardiovascular disease, cognitive decline, organ damage, immune dysfunction. Some effects might not appear for decades, creating uncertainty that never ends. You sacrificed your health for a mission that might not even be remembered in 50 years. Assuming you survive everything and return to Earth, readjustment to normal life will be brutal. You've been isolated for 3 years. Society has moved on without you. Technology has advanced. Cultural references have changed. People you knew have married, divorced, had children, changed careers. You've missed everything. Your friends have formed new friendships. Your family has adapted to your absence. You're a stranger returning to a world that doesn't quite need you anymore. The reverse culture shock might be worse than the isolation was. Your body might never fully recover. Physical therapy could take years. Some astronauts experience permanent vision changes from spaceflight. You might have chronic pain from skeletal damage, fatigue from cardiovascular problems, cognitive issues from radiation exposure. You're in your 30s or 40s, but your body feels decades older. The Mars mission has aged you prematurely in ways medicine can't reverse. Financially, you're probably ruined unless your agency provides exceptional support. 3 years out of the workforce. Medical expenses for ongoing treatment. Possible disability if you can't return to your previous career. The prestige of being a Mars astronaut might open some doors, but it doesn't pay medical bills or compensate for lost earning years. You might spend the rest of your life dealing with consequences of a mission you can't undo. The question becomes unavoidable. Was it worth it? You contributed to human knowledge. You advanced space exploration. You inspired people. But at what personal cost? Your health, your relationships, years of your life, possibly your ability to ever feel normal again. The achievement feels increasingly hollow as you deal with chronic pain and medical appointments, and the reality that your sacrifice benefited humanity abstractly while destroying you specifically. Some Mars advocates dismiss these concerns as cowardice or lack of vision. They argue that exploration requires sacrifice, that progress demands risk, that someone must go first regardless of cost. But there's a difference between calculated risk and suicide mission, between exploration and exploitation, between advancing humanity and throwing away human lives for symbolic victories. The reality is that current technology cannot safely return humans from Mars. Maybe future advances will change that equation. Better radiation shielding, artificial gravity, advanced propulsion, medical treatments that prevent or reverse the physiological damage. But those advances don't exist yet. Sending people to Mars with current technology means accepting that they might never come home. And if they do make it back, they might wish they hadn't. The ethical implications of Mars missions demand serious examination before we commit to sending anyone. Space agencies and private companies consistently frame Mars exploration as humanity's destiny, an inevitable next step in our species' evolution. But destiny isn't a moral justification for human sacrifice. Informed consent becomes questionable when you're recruiting people for missions where the risks aren't fully understood because we've never done this before. How can anyone truly consent to unknown dangers? Astronaut selection for Mars missions raises uncomfortable questions about who gets chosen and why. Young candidates without families are preferred, which effectively means selecting people with fewer earthbound attachments to mourn their loss or sue if things go wrong. Is that pragmatic planning or predatory recruitment? The psychological profiles required for Mars missions favor individuals who can tolerate extreme isolation and deprivation. But those same traits might make someone less likely to abandon a failing mission even when they should. Space agencies emphasize that astronauts volunteer knowing the risks. True, but there's a difference between accepting calculated risks and signing up for what amounts to a probable death sentence with current technology. Test pilots accept risk, but they're testing vehicles designed with realistic safety margins based on decades of engineering knowledge. Mars missions lack that foundation. We're essentially asking people to beta test technologies that have never been proven at scale, in an environment where failure means death. The psychological screening process for Mars missions might actually select for people most vulnerable to the mission's dangers. Extreme risk tolerance, willingness to accept isolation, comfort with uncertainty. These traits help you get selected, but might make you more likely to ignore warning signs that something's going wrong. Someone who recognizes when a situation has become unacceptably dangerous might never make it through selection, because that healthy self-preservation instinct disqualifies them. Financial incentives complicate the ethics further. Private companies developing Mars missions aren't doing it from pure scientific curiosity. They're seeking profit, publicity, and market dominance. When commercial interests drive exploration, cost-cutting becomes tempting. Safety margins get thinner. Backup systems get eliminated to save weight and money. The pressure to launch on schedule regardless of readiness increases because investors demand returns. Astronauts become expendable assets in a business plan. Government space agencies face different but equally problematic pressures. Political cycles create urgency to achieve milestones before administrations change. National prestige motivates risky decisions. Competition with other nations or private entities pushes timelines faster than safety allows. The space race to Mars could replicate Cold War dynamics where political objectives override rational risk assessment. History shows that when prestige is at stake, governments accept casualties that would be unacceptable in other contexts. The impact on astronauts' families receives insufficient consideration. A 3-year mission means missing births, deaths, weddings, illnesses, and countless ordinary moments that constitute family life. Children grow up without a parent. Spouses become effectively single. Parents age without their child present. And if the astronaut dies on Mars or during return, their family experiences a prolonged public death they're powerless to prevent. Mission Control watches telemetry as someone's loved one suffocates, starves, or dies from radiation exposure millions of miles away. The psychological burden on Mission Control creates another ethical dimension. Engineers and flight controllers will make decisions that directly determine whether astronauts live or die. Communication delays mean they'll watch disasters unfold without ability to intervene. They'll analyze data knowing their recommendations might send people to their deaths. The psychological toll on ground teams after mission failures could be devastating. Apollo 1 and Challenger already demonstrated how mission failures traumatize ground personnel. A Mars mission failure would be worse because the death would be slower, more prolonged. Resource allocation presents a massive ethical problem that Mars enthusiasts conveniently ignore. The estimated cost for a single Mars mission ranges from $100 billion to $1 trillion depending on architecture. That money could eliminate malaria, provide clean water to billions, fund cancer research, address climate change, or solve countless problems affecting actual living humans right now? Is sending a handful of people to Mars worth more than saving millions of lives on Earth? The counterargument claims that space exploration drives innovation that benefits everyone. Tang and Velcro, right? Except that's mostly mythology. The return on investment for space technology is poor compared to direct research funding. If we want better water purification, fund water purification research. If we want advanced materials, fund materials science. The spin-off benefits of Mars missions don't justify the cost when that same money could fund targeted research more efficiently. Mars missions also represent an unconscious admission of defeat regarding Earth. The implicit message is that we've given up on solving terrestrial problems, so we're looking for an escape hatch. But Mars isn't a backup planet. It's a lifeless rock, with no breathable atmosphere, no liquid water, and radiation levels that will kill you. If we can't maintain Earth, a planet literally designed by billions of years of evolution to support life, we certainly can't terraform Mars into something habitable. The long-term vision of Mars colonization raises even darker ethical questions. Establishing a permanent Mars settlement means creating a population of humans who will never experience Earth. Children born on Mars will develop in 38% gravity, affecting their skeletal structure, muscle development, and cardiovascular systems in ways that might make them unable to ever visit Earth. They'll be adapted to Mars and trapped there. Is it ethical to create humans who are prisoners of their birthplace? Mars colonists would live under conditions that resemble nothing so much as indentured servitude. Every resource must be rationed. Every moment of life depends on functioning technology. The social structure would necessarily be authoritarian because survival depends on strict compliance with protocols. Individual freedom becomes a luxury no one can afford. You're describing a labor camp on another planet, not a thriving civilization. The genetic implications of a Mars population deserve consideration. Small founding populations experience genetic bottlenecks and inbreeding effects. The Mars population would need careful genetic management to remain viable long-term, which implies controlled reproduction. Who decides who breeds with whom? What happens to genetic diversity after several generations? Are we creating a separate branch of humanity that will diverge from Earth humans over time? Legal frameworks for Mars are virtually non-existent. The Outer Space Treaty of 1967 prohibits national appropriation of celestial bodies, but is vague on private ownership and jurisdiction. Who has authority over Mars colonists? What laws apply? If someone commits a crime on Mars, which government prosecutes them? If corporations establish settlements, do they effectively become sovereign entities? The legal vacuum creates opportunities for exploitation and abuse, with no clear path to justice. Property rights on Mars will create conflict. If private companies invest billions in Mars infrastructure, they'll claim ownership of land, resources, and facilities. But under what authority? The first Mars settlements might resemble company towns from the Industrial Revolution, where corporations controlled housing, food, and employment, effectively owning the workers. History shows how that ended, with exploitation, abuse, and eventually violent labor conflicts. Environmental ethics present an interesting paradox. Mars has no life, so there's nothing to protect environmentally, right? Except we don't actually know that for certain. Subsurface water might harbor microbial life. Human presence would contaminate Mars with Earth organisms, making it impossible to study Mars's pristine state. we could destroy evidence of past or present Martian life before we even discover it. The scientific value of an uncontaminated Mars might exceed the value of human exploration. Planetary protection protocols exist, but are difficult to enforce. Sterilizing everything sent to Mars is expensive and time-consuming. Private companies might cut corners. Once humans land, preventing contamination becomes impossible because humans are walking bags of microbes. Every surface we touch, every breath we exhale, every waste product we generate spreads Earth life across Mars. We might be committing xenocide against organisms we haven't even detected yet. The psychological effects of knowing you're destroying an alien world shouldn't be dismissed. Some astronauts report profound shifts in perspective after seeing Earth from space, the overview effect. What happens psychologically when you're the first to contaminate another planet? When your footprints destroy pristine formations that existed for billions of years? The guilt and responsibility might be crushing for people with environmental awareness. Religious and cultural perspectives on Mars missions vary wildly and often get ignored in Western planning. Some belief systems consider space exploration hubristic or sacrilegious. Indigenous perspectives on land and stewardship don't easily map onto colonizing other worlds. If Mars missions are framed as representing humanity, whose humanity? Whose values? Whose cultural framework? The assumption that Mars exploration is universally desired reveals Western cultural imperialism. The representation of Mars missions in media and popular culture creates unrealistic expectations. Movies show heroic astronauts overcoming obstacles through determination and ingenuity. Reality would be far grimmer. Slow death from radiation, suffocation, starvation, equipment failures that no amount of cleverness can overcome. Entertainment has conditioned the public to expect happy endings and miraculous rescues. Mars won't provide those. Public support for Mars missions is shallow and evaporates quickly when actual costs become clear. Polls show majority support for space exploration until you mention the price tag. Support drops dramatically when people understand that Mars funding means cutting other programs. The political sustainability of Mars missions is questionable. One administration enthusiastically funds Mars, the next cancels it. Starting a Mars mission without sustained decades-long commitment guarantees failure and wastes whatever money was already spent. The opportunity cost of Mars missions extends beyond money to human talent and resources. The engineers, scientists, and support personnel working on Mars could be solving Earthbound problems instead. Every hour spent planning Mars logistics is an hour not spent on climate change, disease, poverty, or education. We're allocating our best minds to a vanity project while urgent problems go unsolved. Alternative approaches to space exploration make more sense. Robotic missions provide enormous scientific return without risking lives. AI and automation continue improving, making robots increasingly capable. The James Webb Space Telescope has revolutionized astronomy without sending anyone anywhere. Mars rovers have operated for years, traveling miles, analyzing rocks, and sending back data, all without life support, food, or return vehicles. Why not just send better robots? The counter-argument claims that humans can adapt and problem-solve in ways robots can't. True for now, but the gap is closing. And even if humans offer advantages, those advantages don't justify the cost and risk. A human might notice something a robot would miss, but is that worth the $1 trillion price tag and probable deaths? The cost-benefit analysis doesn't support human missions when robots keep getting better and cheaper. Virtual reality and telepresence offer middle-ground solutions. Astronauts in orbit around Mars could remotely operate surface robots without the communication delay that Earth-based control suffers. You get human decision-making without landing anyone on the surface. The astronauts remain in relative safety while still participating directly in exploration. It's not as viscerally satisfying as boots on Mars, but satisfaction shouldn't drive policy. The fixation on Mars specifically reveals questionable priorities. If the goal is human expansion into space, the Moon makes more sense as a testing ground. 3-day travel time instead of 9 months. Real-time communication instead of 20-minute delays. Earth is visible in the sky, providing psychological comfort. Rescue is actually possible if something goes wrong. Every argument for Mars applies to the Moon with significantly reduced risk and cost. Venus's upper atmosphere might be more hospitable than Mars's surface. At 50 kilometers altitude, Venus has Earth-like pressure and temperature. Floating habitats could exploit this. The engineering challenges are different, but potentially more solvable than Mars surface habitation. But Venus lacks the romantic appeal of Mars, so it gets ignored despite possibly being the better option for human presence. Asteroid mining presents better economic justification than Mars colonization. Near-Earth asteroids contain valuable metals and water. The resources could support space infrastructure and generate actual profit. The environment is harsh, but the destinations are closer and the mission durations shorter. If the goal is space resource utilization, asteroids make more economic sense than Mars. The fundamental question remains: why Mars at all? Strip away the romance, the science fiction imagery, the sense of destiny. What's the actual justification that withstands scrutiny? Scientific research? Robots do that better. Human survival? Mars can't support human civilization with current technology. National prestige? That's not a moral justification for risking lives and spending trillions. Economic development? There's no plausible business case. The Emperor has no clothes, but we're too invested in the mythology to admit it. The most damning evidence against Mars colonization comes from those who've studied it most carefully. MIT researchers ran detailed simulations of Mars settlement scenarios using existing technology. Their conclusion: colonists would begin suffocating after approximately 68 days. The problem isn't lack of oxygen, it's too much. Growing enough food to sustain a colony produces oxygen levels that become toxic. The habitat would need to vent excess oxygen constantly, but that means losing precious resources that took enormous energy to produce. The simulation assumed perfect conditions, no equipment failures, ideal crew health, flawless execution. Even then, death within 70 days. Reality would be worse. NASA's own assessments tell a similar story. The agency has identified over 30 major technical challenges that must be solved before human Mars missions become feasible. Not minor issues, fundamental problems without current solutions. How do you land 50-ton payloads on Mars when the largest successful landing was 1 ton? How do you produce 1,200 tons of propellant from Martian resources when we've never manufactured fuel on another planet? How do you protect astronauts from radiation doses that exceed career limits? Each question represents years of research and billions in development costs. Many may not have solutions at all. The Mars One project collapsed spectacularly, illustrating the gap between vision and reality. The Dutch non-profit promised to establish a permanent settlement by 2025 using only existing technology. They attracted thousands of applicants willing to die on Mars. The plan fell apart when engineers examined it seriously. Funding never materialized because the business model made no sense. The technology wasn't as ready as claimed. The timeline was pure fantasy. Mars One declared bankruptcy in 2019, leaving behind nothing but disappointed would-be colonists and proof that enthusiasm doesn't overcome physics. Consider the return journey problem specifically. Producing rocket fuel on Mars requires extracting over 1,000 tons of water from Martian soil, then processing it through chemical reactions we've never performed at scale on another planet. The Sabatier reaction can theoretically convert Martian CO2 and hydrogen into methane fuel, but the engineering challenges are staggering. You need power sources that function during months-long dust storms, equipment that operates in extreme cold without maintenance, robots capable of mining operations at depths requiring tens of meters of drilling. None of this exists, and if any component fails, the astronauts are simply stranded. There's no backup plan when you're on Mars. The psychological dimension might be the most underestimated factor. Antarctic research stations provide our best analog for isolated, confined environments. Even there, with the knowledge that rescue is possible and tours of duty are limited, psychological issues arise regularly. Depression, interpersonal conflicts, cognitive decline. Mars would be exponentially worse. No rescue possibility, no rotation home. Earth visible as a tiny blue dot, impossible to reach. Communication delays of up to 44 minutes round trip, making real conversation impossible. Your family aging 20 minutes in the past while you're trapped in a tin can on a frozen desert. Studies of cosmonauts identified the factors they rated most concerning for Mars missions: isolation, monotony, communication delays, leadership conflicts, and cultural misunderstandings. These were professional astronauts with extensive training, anticipating missions measured in months. Imagine permanent settlement, years stretching into decades. The same 6 or 8 people forever. No privacy, no escape, no new faces. Historical precedents from isolated communities suggest this ends badly. Cabin fever, paranoia, violence. On Mars, you can't separate conflicting parties. You're all trapped together until death. Medical emergencies become death sentences. Appendicitis kills you. A broken bone that becomes infected kills you. Kidney stones, dental problems, strokes. Anything requiring more than basic first aid likely proves fatal. The communication delay prevents Earth-based doctors from providing real-time guidance. Telemedicine with 20-minute lags is essentially useless for acute situations. You could bring a surgeon, but one surgeon can't cover every specialty, and surgeons need functioning operating rooms, which need reliable power and sterile conditions and medications and equipment. A Mars habitat can't replicate a hospital's capabilities. People will die from conditions that are routine to treat on Earth. The long-term physiological effects of 0.38 grams remain unknown because we've never studied them. All our data comes from either microgravity or 1G. Mars sits in between, and we can only speculate about the consequences. Initial evidence suggests it won't be good. Bone density loss, muscle atrophy, cardiovascular changes, vision problems. These occur in microgravity despite exercise countermeasures. Mars provides more gravity than 0G, but probably not enough to prevent deterioration. Astronauts might adapt to Mars only to become incapable of ever returning to Earth. Their bodies could change in ways that make 1G unbearable or impossible to survive. Children born on Mars would face even stranger fates. Developing in 0.38G might produce bodies fundamentally different from Earth humans. Weaker bones, different muscle structure, cardiovascular systems adapted to lower gravity. These children could never visit Earth. The planet their parents came from would be literally uninhabitable for them. They'd be a new species, Homo martianus, trapped on their birth world. This raises profound ethical questions about creating humans who are prisoners by biology. The economics remain fantastical, despite decades of trying to make them work. No business case for Mars withstands scrutiny. There's nothing to mine that justifies transport costs. No products to manufacture that couldn't be made more cheaply on Earth. No services to provide that generate revenue. Tourism? Maybe eventually, but not supporting a permanent settlement. The Antarctic Treaty allows tourism to Antarctica, yet no permanent private settlements exist there despite being far more hospitable and accessible than Mars. If Antarctica can't sustain private settlements, Mars certainly can't. The opportunity cost grows more troubling the longer you examine it. $1 trillion over 20 years. That's the conservative estimate for establishing a Mars settlement. What else could that buy? Complete renewable energy transformation of multiple countries, elimination of several major diseases, ocean cleanup, poverty reduction, education programs for millions. The entire annual budget of NASA is about $25 billion. A Mars settlement would consume that much every year for 2 decades. And that's assuming everything goes perfectly, which it won't. The engineers and scientists working these problems aren't optimistic. Behind closed doors, away from public relations messaging, they acknowledge the challenges might be insurmountable with current technology. We need breakthrough innovations in propulsion, radiation shielding, life support, materials science, and medicine. Each breakthrough requires unpredictable research timelines, maybe 20 years, maybe 50, maybe never. The public narrative of Mars settlements by 2030 or 2040 is marketing, not engineering assessment. Even assuming we solve every technical problem, the question remains, should we? The argument that humanity needs a backup planet assumes Earth could become less habitable than Mars, which is absurd. The worst climate change scenarios, the most devastating nuclear war, the most catastrophic pandemic, all leave Earth vastly more livable than Mars will ever be. Earth with a runaway greenhouse effect is still better than Mars. Earth after nuclear winter is still better than Mars. We're not preserving humanity by going to Mars. We're creating an expensive, dangerous theme park for a few dozen people, while billions remain on the only planet that actually sustains human life. The Mars obsession reflects something deeper than practical goals. It's mythology dressed as engineering. The frontier spirit, manifest destiny, humanity's drive to explore. These narratives sound inspiring, but don't justify the reality of what we're proposing. We're not talking about sailing to a new continent. We're talking about condemning people to short, difficult lives in an environment actively trying to kill them for no practical benefit at staggering cost. The people who volunteer for one-way Mars missions often describe it as the ultimate adventure, a chance to be part of history. That's legitimate from their perspective. But society shouldn't enable their sacrifice when it serves no purpose beyond spectacle. We don't celebrate other forms of pointless self-destruction. A Mars settlement would be the most expensive suicide mission in history, and we shouldn't pursue it just because volunteers exist. The alternative path forward is obvious. Continue robotic exploration. Rovers and landers keep getting better. The Perseverance rover has been operating for years, covering miles of terrain, analyzing samples, gathering data that humans couldn't safely collect. The James Webb Space Telescope has revolutionized our understanding of the universe without risking anyone. This approach provides better science per dollar and zero risk to human life. As AI and robotics improve, the gap between human and robotic capabilities will narrow further. If the goal is expanding human presence into space, the moon makes infinitely more sense. 3 days away instead of 9 months. Real-time communication. Visible Earth providing psychological comfort. Actual possibility of rescue. Lower gravity, but still reduced enough to study long-term effects. Ice at the poles for water and fuel. And if we can't make the moon work, we definitely can't make Mars work. The moon should be our testing ground, our learning environment. Master lunar settlement first, then consider more distant goals. But the moon lacks the romance of Mars. It's been done, in the sense that we've been there. Mars represents the next frontier, the next achievement to unlock. This is emotional reasoning, not logical planning. The moon being boring doesn't make Mars more practical. If anything, it proves we're driven by narrative and imagery rather than sound judgment. The honest assessment is uncomfortable. Sending humans to Mars with current or near-term technology is somewhere between extremely dangerous and simply impossible. The people who go might never come back, not because they choose to stay, but because return becomes impossible once they're there. Equipment failures, resource depletion, medical emergencies, psychological breakdown, any of dozens of failure modes could strand them permanently. And unlike Mars rovers that simply stop functioning, stranded humans die slowly, fully aware of what's happening. This isn't pessimism, it's realism. The difference matters because optimism that ignores reality gets people killed. The engineers working these problems understand the risks. The challenge is getting the public and policymakers to understand them too. Mars settlement is possible in the same sense that anything not violating physics is possible. But possibility doesn't mean feasibility, and feasibility doesn't mean wisdom. The fascination with Mars will likely continue regardless of practical concerns. Humans are drawn to grand challenges and distant horizons, but we should be clear about what we're actually proposing. Not a glorious new chapter in human history, a dangerous, expensive, likely fatal undertaking that serves mythological needs more than practical ones. The people who go to Mars might never come back because Mars is fundamentally hostile to human life in ways we cannot adequately overcome. That's not a challenge to be conquered through determination. It's a physical reality we need to accept. Human Mars missions will eventually happen because humans are ambitious and occasionally reckless. But they shouldn't happen soon. They shouldn't be permanent settlements. And they absolutely shouldn't be marketed as anything other than what they are. Extremely risky expeditions with unclear benefits and high probability of failure. The astronauts deserve that honesty. The public funding it deserves that honesty. And the engineers solving impossible problems deserve that honesty most of all. The cold truth emerges from beneath layers of optimism and propaganda. We're not ready for Mars. Not technologically, not psychologically, not economically, not ethically. The gap between what we can do and what Mars demands is vast, possibly unbridgeable, with foreseeable technology. Every technical challenge compounds every other challenge. You need reliable power systems to manufacture fuel, but power systems require maintenance you can't perform during dust storms. You need water extraction to make fuel, but extraction requires drilling equipment that doesn't exist in Mars-capable form. You need healthy astronauts to operate equipment, but the radiation and reduced gravity are destroying their bodies from the moment they arrive. You need psychological resilience to handle isolation, but the isolation itself erodes psychological resilience. There's no single failure point because everything is a potential failure point simultaneously. The return journey represents the ultimate test of our honesty about Mars missions. Can we actually bring people back? The answer right now is maybe. Maybe if everything works perfectly. Maybe if no equipment fails. Maybe if the astronauts stay healthy and sane. Maybe if fuel production succeeds. Maybe if the return vehicle survives months of Martian conditions. Maybe if Earth re-entry doesn't kill them. That's too many maybes when lives are at stake. Some argue that exploration always involves risk, that progress demands sacrifice. This minimizes the difference between calculated risk and recklessness. Test pilots accept risk, but they're testing aircraft designed with safety margins based on decades of engineering knowledge. Mars missions lack that foundation. We're asking people to beta test technologies in an environment where failure means death, with no possibility of rescue for unclear benefits. That's not brave exploration, that's poorly planned sacrifice. The psychological toll deserves more attention than it receives. We focus on radiation and bone loss because those are measurable, quantifiable. But watching Earth become a pale blue dot, knowing you might never return, experiencing total isolation for years, those psychological factors could break people in ways that end the mission even if all the equipment functions perfectly. A psychologically broken crew can't maintain equipment, can't make rational decisions, can't survive. Mental health isn't secondary to physical challenges. It might be the primary challenge. Medical capabilities on Mars will be primitive compared to Earth. No imaging equipment, no specialists, no surgical suites, no blood banks, no pharmaceuticals beyond what you brought. Every medical situation becomes a potential death sentence. Appendicitis kills you. Kidney stones kill you. Infections kill you. Dental emergencies kill you. The communication delay prevents Earth-based doctors from helping in real time. You're on your own with whatever medical knowledge your crew possesses, which won't be enough when someone needs emergency surgery or develops a condition requiring specialized treatment. The economic case remains non-existent despite decades of trying to manufacture one. Nothing on Mars justifies the cost of getting there. No minerals worth mining, no products worth manufacturing, no services worth providing. The only argument is exploration for its own sake, which is fine for robotic missions, but questionable justification for risking human lives and spending trillions. Society makes cost-benefit calculations constantly. We don't fund every possible research direction because resources are limited. Mars fails the cost-benefit test by enormous margins. The opportunity cost becomes more troubling the deeper you examine it. That $1 trillion could eliminate diseases, provide clean water, fund education, address climate change, solve problems affecting billions of actual humans right now. Instead, we're proposing to spend it sending a handful of people to a dead world where they'll probably die. The engineers and scientists working on Mars could be solving terrestrial problems. Every hour spent on Mars, logistics, is an hour not spent on urgent challenges facing humanity today. Alternative approaches offer better outcomes. Robotic missions provide excellent science without risking lives. As AI and robotics improve, the capabilities gap between humans and robots narrows. The James Webb Space Telescope revolutionized astronomy without sending anyone anywhere. Mars rovers have operated for years, covering significant distances, analyzing samples, gathering data humans couldn't safely collect. Why not invest in better robots instead of risking human lives? The Moon presents a more logical stepping stone if human space presence is the goal. 3-day travel time instead of 9 months. Real-time communication instead of 20-minute delays. Earth visible in the sky, providing psychological comfort. Actual rescue possibility if something goes wrong. Lower gravity, but still reduced enough to study long-term effects. If we can't make lunar settlement work, we definitely can't make Mars work. The Moon should be our testing ground. But the Moon lacks Mars's romantic appeal. It's been done. Mars represents the next frontier, the next achievement. This is emotional reasoning, not logical planning. We're driven by narrative and imagery rather than sound judgment. The mythology of Mars exploration has overtaken practical assessment of whether we should actually do this. One-way missions might be more honest about the reality we're facing. Buzz Aldrin advocates for Mars-to-stay missions where astronauts go permanently. This acknowledges that return might be impossible with current technology, but it also means asking people to exile themselves forever, condemning them to short lives in a hostile environment for no clear purpose beyond the symbolism of human presence on Mars. That's not exploration. That's human sacrifice dressed in spacesuits. The ethical problems multiply when you consider children born on Mars. They develop in reduced gravity, their bodies adapting in ways that might make Earth uninhabitable for them. Creating humans who are prisoners of their birthplace raises profound moral questions. Are we establishing a settlement or creating a permanent underclass of humans trapped on Mars by their own biology? The technological readiness simply isn't there. NASA has identified dozens of major challenges without current solutions. Landing large payloads, manufacturing fuel from Martian resources, protecting against radiation, maintaining equipment during dust storms, growing food in toxic soil. Each problem requires breakthroughs that may take decades or might never come. The timelines companies propose for Mars settlement, 2030, 2040, are marketing, not engineering assessment. Behind closed doors, away from public relations messaging, engineers working these problems express serious doubts. They know the challenges. They understand the risks. The gap between public optimism and private assessment is troubling. We're selling a vision that experts know we can't deliver with current or near-term technology. The Mars One collapse illustrated this gap perfectly. Thousands of people volunteered for a one-way mission. The plan sounded feasible to the public. Engineers examined it seriously and found it completely unworkable. The project went bankrupt, leaving nothing but disappointed volunteers and proof that enthusiasm doesn't overcome physics. That failure should have prompted more skepticism about Mars settlement timelines. Instead, New proposals emerge making similar promises. The fundamental question remains unanswered. Why Mars? Strip away the mythology and what's left. Scientific research happens better with robots. Human survival isn't ensured by a Mars colony that can't sustain itself. National prestige is a poor justification for risking lives. Economic development has no plausible business model. We're pursuing Mars because the narrative is compelling, not because it makes practical sense. The honest assessment is that anyone who goes to Mars with current technology might never come back. Not because they choose to stay, but because return becomes impossible once they're there. Equipment fails, resources run out, bodies break down, minds deteriorate. The return window arrives, but the capability to use it doesn't exist. They're stranded, dying slowly on a frozen desert, fully aware that rescue isn't coming because rescue can't come. That's the reality beneath the inspirational speeches and glossy promotional videos. This isn't meant to crush dreams or discourage exploration. It's meant to inject realism into discussions dominated by optimism that ignores practical constraints. Mars missions will probably happen eventually because humans are ambitious and occasionally reckless. But they shouldn't happen soon, shouldn't involve permanent settlements, and absolutely shouldn't be marketed as anything other than extremely risky expeditions with high probability of failure. The astronauts who volunteer deserve honesty about what they're facing. The public funding these missions deserves honesty about likely outcomes. The engineers solving impossible problems deserve honesty about whether their solutions can actually work. Right now, we're not providing that honesty. We're selling mythology as engineering, ambition as capability, hope as planning. Mars will still be there in 50 years, 100 years. It's not going anywhere. We can wait until technology actually matches our ambitions. We can perfect systems on the moon first. We can send better robots in the meantime. We can be honest about current limitations instead of pretending they don't exist. The people who go to Mars might never come back, because Mars is fundamentally hostile to human life in ways we cannot adequately overcome with foreseeable technology. That's not a challenge to be conquered through determination. It's a physical reality we need to accept. Accepting it doesn't mean giving up on Mars. It means being honest about timelines, risks, and the difference between what's possible and what's wise. The universe is patient. Mars has been waiting for 4 billion years. It can wait a few more decades while we figure out how to actually do this right. Because sending people on missions they can't survive isn't exploration. It's tragedy dressed as progress. And we're better than that, even if our mythology sometimes suggests otherwise.